Okay, so we're going to talk a little bit more about how we can do some more advanced operations with our user-defined functions. First, we'll talk about attributes. So properties or attributes of a function are stored within a function call or method within S4. We can get at what the attributes of an object are by running the attributes function, or we could use the attr shortcut function to get at just particular attributes of an object instead. It also will set particular attributes of an object. So sometimes an object has many attributes and we do not actually need to observe all of them, let's say. The mode and the length are also intrinsic attributes that are not going to be returned by our attributes call function, and the class attribute is not returned if the object has some sort of implicit class-like matrix. So this should all be thought about as we use this attributes or attr function. So let's look at this power function, and we'll look at it in the code in just a moment. But what this is going to do is just going to compute the power of a number x to a certain power n. Okay, so we could define this. We're defining this class as being new, and we're specifically defining the attribute of the call portion of the function, of the method, I should say, to just match the call. So let's take a look at what happens if we run this. Let's go to the code. I think it'll be easier to see if we just go straight to code. Okay, so here we run the function, okay, for power. So now it's defined. It's going to have, we could actually view the contents and we can see all of the structure that we just defined for that power function. We can compute it, and notice what this is going to do is we can see the correct values there that are what we get, but we also see the attribute for the call provided as well as the class. If we then run the attributes, let me try that again. I messed that up. If we then run the attributes function on that object y, because remember y is an object that now has this class new and was run through the power function, we see that the class is new and we see the call. Okay, if we then run just attr call, we just see the call. All right, so this is a way of controlling how the attributes gets reported for a particular method within this environment. Here are some of the other functions that are useful when you're writing more advanced functions within R. Eval is going to evaluate an unevaluated expression. Sometimes it's best to set up the code and then evaluate it at the end of your function. Substitute is going to return an unevaluated expression with substituted variables found in the current environment. Quote is just going to return a quote of your unevaluated argument. Sometimes that's really useful. I use this a lot for defining function calls within a program where I want it to be automatically defined by the algorithm. Parse is going to convert character strings to some parsed expression that is going to be unevaluated. And then dparse will turn that unevaluated expression into a character string so you can get back at it. A little hard to understand until we see application. Let's go to the code and see this worked out. Here I'm defining a matrix .n, and what this is going to do is just take the nth power of a matrix A. So we input a matrix A and then a power, okay? And what this is going to do is it's going to evaluate what that would be. So for example, if x looks like this, so x is just a simple 1, 2, 3, 4, 2 by 2 matrix. I could run x where n is equal to 5 and the matrix A is equal to x. I could run that and I get back this 2 by 2 matrix. Now what is that? Well, it's actually what I have scripted right down here below. It is x, matrix multiplication x, matrix multiplication x, matrix multiplication x, matrix multiplication x. And in fact, I can show that to you. And we get the same result. But this is where the eval and parse statement come into play, because we need to be able to write this character string and then evaluate it at the end. So notice here, paste is just taking and creating A and repeating it 5 times, where we collapse it with that matrix multiplication in between each value. So it's creating this string right here, and it's going to save it as AN. Then we take that text AN, we parse it, which means we return it unevaluated, but ready to be evaluated as a non-character string, and then we evaluate it. So at the very end, this finally gets computed. Okay, little complicated, but this is really useful for cases where the user may input, I want to have, say, an nth degree polynomial with these variables, and then you can actually create the polynomial function using some kind of combination of a paste expression, a paste function, and then the eval and parse to take that nice character string that you've created using the paste function, turn it into a non-character string, and then evaluate it at the conclusion of the function. So this is very useful stuff. Okay, a little bit more. Deparse and substitute are often used to, say, pull apart the contents of a argument. Okay, so here we have something where we are going to enter an x and we want to get the mean. And it's pretty simple. We just want to compute the mean, but we actually also want to know what it is that we're getting the mean of. So let's say we have some test scores, and then we run get mean scores. We want to be able to see this like this. So notice it says the mean of. Well, we need to know what var is. Well, that's where deparse comes in, because remember, substitute is going to create a character string of substituted values. So it's going to take the name of x, which in this case is scores, and substitute that. And then deparse turns it into a character string. So it gets treated as a character string down here. And then x, though, is going to be numeric vector. We have a little test here to ensure that it is, in fact. And then we can compute it down here. We don't need the eval down here, by the way. You could put that, but it would be redundant because mean has the eval implicit within it. So here we get the mean scores as 86.8, which is the mean of those scores right there. If we then say got grades and it was a vector of grade scores like this, it would not work because grades is not numeric. So that error check works. Finally, we need to sometimes do error recovery when we are working with functions. Let me get this back. Okay, so let's say you're running a very long algorithm or a simulation where we don't want to just stop running because an error occurs. Maybe it's because we get some ill-defined data, but we'd like to record that that data existed and move on to the rest of the operations within the simulation or the algorithm. We'd like the program to make note of the error and keep running, of course. So try is a good general function written within R that helps you do this. So it has two arguments. Expression, which is the expression of that you need to catch as an error. So the function maybe that could be called that could result in an error, for example. And then a silent argument. So this is an indicator argument that tells whether or not to report the error or not to report. The function try is going to generally evaluate this expression and then trap any errors that occur during the evaluation. It will return the value of the expression if it occurs with no error. But if an invisible object of class try error contains if it fails. So silent equal true means the error message will get suppressed. Usually we want silent to be equal to false, so we catch that error. Try catch is a more general approach for catching and handling errors that allows for warnings and so forth. Suppress warnings will evaluate expressions and ignore warnings. So sometimes we know certain things will happen and we want to evaluate it anyway, so we can suppress the warnings. So here's an example. Let's see. We want to study the effect of very small uniformly distributed covariates on least squares estimation. So here's our parameter setup, and here's our simulation. We generate some data. We put the data all together, then we evaluate it. So notice this is x beta plus the error. Error is that normal 0, 1 vector. And then we're going to estimate the parameters. So this is the least squares formula right in here, okay? Notice the least squares formula is contained within the try function, okay? This, I can't really click on this, but this whole thing gives you that least squares solution. X prime x inverse, x prime y. It's that least squares formula. Here, this is going to estimate the parameters. If t returns try error, then we just move on to the next beta hat, and we get back that there was an error. Else, we return back what the contents of t are, which will be the estimated parameters for beta. Okay, so we can then apply at the end of this what the average is for all of these, and also report the number of failed iterations at the end. Let's take a look at this now within the code. Okay, so here's the code to run this simulation and use this try function to catch some errors. So it's intentionally set up so we should have a good number of errors when we run this. So our sigma, its unit variance for the error, beta is 1, 2, so 1 for the y-intercept, 2 for the slope. Our sample size is 100, and we're going to repeat this simulation 1,000 times. So here we set up the beta hat so that it will, right now it's just initialized. You can take a look at it. It's just going to contain all of those values so that we can store those results. Then we walk through the for loop. So let's just go through that for loop. And then we can look at the results. So where we saw an NA, whoa, what happened here? Let's try this again. Okay. So let me see what I got the first time I printed this. Oh, I can't see it because of the vector. So what we're getting here is our results for over all of those iterations. We can actually take a look at beta hat and see what it looks like. So we can see that we get a lot of values for that y-intercept that's quite close to 1. We're getting a lot of unreasonable values here for our slope parameter. The first time I ran this, it was very close to 2. Let me think about what could be going on here. But notice there were lots of cases, regardless, there are lots of cases where we get NAs. And this is because right here, when it gets a try error result, it's going to return NA. And otherwise, it gets back those values that were estimated. So this allows us to report back those cases. And in fact, the number of failed iterations is 87 out of the 1,000. So there's 87 cases, 87 cases where we have an NA. Let's stop there and we can go on and take a look at the last bit of advanced programming.